In today's video, we're going to talk about the final sort of chosen application of first-order differential equations, which is that of some simple circuits. Now, I'm not going to sit here and pretend like I am the expert on circuits and the associated terminology. Probably most of you know more about this from your physics courses than I know at the moment. But just in case, I'm going to walk you through a few basic pieces of terminology and my sort of rough understanding of what that terminology means. So in a circuit, electrons are quote-unquote flowing through the circuitry. You can argue with me about flow of electrons versus flow of electron holes. I don't want to get into that. Now, I think about electrons flowing through a circuit as being akin to maybe water flowing or the flow of traffic. Voltage refers to the quote-unquote pressure that pushes the electrons through a circuit. And impressed voltage refers to the voltage that's applied, the pressure that is applied to a circuit or a device, for example, from a battery. Now, circuits at their most basic have a couple of different sort of objects attached to them. Things that are sources of pressure or sources of voltage are called cells. And things that cause voltage drops are called components. When someone says to me voltage drop, I'm kind of imagining that water is flowing and then it encounters a dam. And then after it hits that dam, you see the water flowing at a lower level after that. And this is my sort of imagination of a voltage drop. In this analogy, the dam would be a component. And components come into rather three varieties: resistors, inductors, and capacitors. Inductors and capacitors store energy either in a magnetic field or in an electric field, whereas resistors dissipate energy usually into heat. Now, the ability of a resistor to dissipate energy is measured by something called resistance, which is usually represented by the capital letter R. The ability of an inductor to convert/store energy in a magnetic field is measured by a quantity called inductance, and that's often called L. And the capacity of a capacitor to store energy in its electric field is measured by a quantity called capacitance. And roughly speaking, the amount of stored energy is called charge. We usually call capacitance by C, is how I usually see this denoted, and charge, roughly speaking, by either a lowercase or uppercase q. So in the case of a simple circuit, which consists of a cell, a source of impressed voltage, a resistor, represented by a little squiggle and an R in a circuit diagram, and an inductor, aptly represented by a coil, then we can obtain a differential equation which relates the impressed voltage coming from this cell, this should be E actually, is more standard, E of t, to the current flowing through the circuit with the resistance of the resistor and the inductance of the inductor. The differential equation is that if you take the inductance and multiply it by the rate of change of current, and add it to the resistance multiplied by the current, then that is equal to the impressed voltage. So this is the differential equation that can be solved for the current represented by the letter I. For example here, consider a simple circuit which is hooked up to a source composed of a 9-volt battery. The circuit has an inductor where the inductance is 1 and a resistor where the resistance is 5. So from that data, let's determine the current I if the initial current is 0. So whether or not you understood my sort of extremely rough explanation of circuitry, you can survive these problems by just reading it carefully and putting the constants into their correct positions. The current represented by I is 0 when no time has passed. The impressed voltage, represented by E, is constant at 8. The inductance, represented by L, is equal to 1. The resistance, represented by R, is equal to 5. And we're solving this for I. So 1 times I prime is meaningless. We can just write I prime. And we're left with a linear differential equation that we can solve, for example, using integrating factors. So setting u of t equal to e to the integral of 5 with respect to time, we get u of t is equal to e to the 5t. And therefore our current satisfies the equation that if I take e to the 5t and multiply it by the current, then that's equal to the integral of the function 8 multiplied by the integrating factor. So if I evaluate that integral, 8 over 5 e to the 5t plus c, I get that the current is equal to 8 over 5 plus c e to the negative 5t. Now, using the fact that the initial current was 0, I get that 0 is equal to 8 over 5 plus c, and therefore c is equal to negative 8 over 5, which implies that the current at time t is equal to 8 over 5 minus 8 over 5 e to the negative 5t. Now we can set up something very similar if we have a circuit which contains only a voltage source, a source of impressed voltage, which again traditionally is called E and not V, and a resistor and a capacitor. So we're dissipating energy and we're storing some energy in an electric field. So in this case, you can set up a differential equation relating the amount of impressed voltage, the resistance of the resistor, the capacitance of the capacitor, and the charge, the amount of stored energy, roughly speaking. In this case, the differential equation is given by the resistance times the rate of change of the charge plus 1 divided by the capacitance times the charge. That is the same thing as the impressed voltage. Once again, whether or not you understand where this comes from or what it means conceptually, you can survive these problems by just putting the constants in the correct place and solving mathematically. So we have a circuit with just a resistor and a capacitor called an RC series circuit. The impressed voltage is constant at 100. The resistor has a resistance of 200. And the capacitor has a capacitance of 0.001. So using that information and using the assumption that the initial charge is 0, let's go ahead and find the charge. Once again, this is an excellent opportunity to use integrating factors. But before I am able to use integrating factors, I need to put this into standard form, which means making sure that Q prime stands alone. So the first thing that I'm going to do is I'm going to rewrite 1 divided by 0.001 as 1000, so that when I divide by 200, I get Q prime plus 5 times Q is equal to 1/2. So just as before, we can set up our integrating factor. Just as before, we can use that to set up an equation that we can solve for Q. 1/2. And we get e to the 5t times Q times the charge is equal to 1/10 e to the 5t plus c, which implies that the charge is equal to 1/10 plus c e to the minus 5t. Just as before, if we set the time and the charge equal to 0 simultaneously to reflect the initial condition, we get c is equal to negative 1/10, and therefore the charge at time t is given by 1/10 minus 1/10 e to the negative 5t. Now, a natural question might be, what if you had a circuit that had all three varieties of component attached? A resistor, a capacitor, and an inductor. It is definitely possible to set up a differential equation in that case as well, a differential equation for the current in that case, but that differential equation ends up being second order. So we're actually going to return to that in a little while after we study how to solve some second order differential equations. That concludes today's material. Briefly went over some basic circuit terminology, and we looked at some differential equations relating some quantities in a circuit, either an RL series circuit or an RC series circuit.